we've talked a little bit about the difficulties of measuring soil moisture and sensors and things like that, and that sensors give us some sort of a relative measure of soil moisture. But the work that I'll be talking about today is sort of taking that relativity away, actually getting some real values of what those soil moistures are telling us, and then how to incorporate that information into a spatial mapping type of framework. So the context of this story, I suppose, is our CSRO purchased a farm just near Boorowa, just outside of Boorowa in 2017, I think. So it's a 290 hectare farm. It's a mixed cropping and grazing, and it's in the southern cropping region. So it's probably what most people might know. It's only 2 hours northeast of here. So in general, for the soil people here, so and Mark sort of said before, it's this sort of gently sort of rolling sort of country, low sort of 1 to 3% type slopes. Most of the soils, depending on the subsoil acidity, that you've got chromosols or curasols, and on the lower parts of the landscape, you start to see more sort of consistent sort of soils, less texture contrast, I suppose. There's quite a bit of mottling in the subsoils as well, and we found also there's quite a lot of gravel in these soils, like 20 to 40% gravel in the soil. So it's one of these things we need to consider in terms of crop water management. Okay, there's a website there to look at some further information about the farm. So in general, what I'll be talking about today is it's a connected story. So it's really about calibration of soil moisture sensors, but to do that, it needs to be underpinned by some soil information, some soil mapping, because that puts things into reality, not relativity. So I'm going to be talking a bit about the digital soil mapping at Boorowa, and how we estimate key soil attributes related to soil moisture, and everyone's been talking about it today. So the key variables are the drained upper limit and the lower limit. In this case, is not necessarily the crop lower limit, but more the 15 bar soil moisture. So or what most people have been saying today is the plant wilting point, I suppose. I'll be talking a bit about the soil moisture sensor network at Boorowa, and then the steps for the soil moisture sensor calibration, and that's all based on the soil information that we've determined for the maps. And then to combine that, to come up with actual spatial mapping, three-dimensionally, of the soil moisture on a daily time step across the farm. It's really it's very much a data-rich exercise, in that we've got all these sensors, we've got all this soil mapping, and how do you sort of bring all those together to come up with some useful types of outputs that even that are going to be used for farming operations, or for precise management of crops across the farm and other places. So the underpinning after the farm was purchased, I suppose, was the establishment of the baseline, the soil map. There's 5 main components of that. There's a reconnaissance type survey. We've got some videos here. So we've got the on the go type vehicle here. It's got a bit of a computer there that combines all the data. But the main thing is it's got these sensors on board. You've got a GPS on the front. There's a gamma spectrometer. On the back is a EM, measuring the conductivity of the soil, and that's basically just driving across the whole farm, generating tight line spacings across the farm, and you're really just collecting all this information that's sort of going to help determine the variability of the landscape that you're driving over. And it's sort of this map there. That's telling us what Mark was talking about before, about the gamma radiometric. So you've got this really high resolution characterisation. It's not necessarily it's not a specific type of soil attribute, but it's a variable that's going to help us understand the variability of the soil. So once we've got that information, we use this sort of proximally sensed data to come up with a sampling plan across the farm, and that data guided our sampling of that, just taking soil cores. And I'll stop that video. And these soil cores, we've got a core scanner, so it's a soil core scanning thing. What it does, it measures the infrared responses of the soil. It's measuring down the core. It's also measuring the density, like the bulk density or the actual density of the soil. So it's usually utilising the relationship between the attenuation and density of the core. So, and that's done at all cores, and that information, it's telling us, from that infrared responses of the soil, it's telling us various attributes of the soil. So we want to know things like what the carbon is, what the texture, pH is, and that that's the technology we're using. That's coupled with some measurement as well. To the next slide. So basically, once we've got all that measurement data, we can start. We're using digital soil mapping type model, which is it's really you're wanting to know the spatial variability of soils, and that's a function of where it is in the landscape. So looking at things like terrain and all these other factors that control the soil variability. So this, for example, once you use this model, that's fitted at the points where we've got the measurements, and then we develop a model, then we can extrapolate that or interpolate it across the whole farm. So in this case here, we've got bulk density at a 5 metre spatial resolution, and this is just showing the surface, but we've also got this at all depths, so it's a three-dimensional characterisation of the soils across the farm. So bulk density is really difficult to measure, but utilising that core scanner, we can actually get really good estimates, really good, high-value estimates across the whole farm. And yeah, same with all other variables, so pH, for example. So that's underpinned by spatial modelling, and it's really sort of establishing that baseline estimate of soil variability across the farm. But that's the key soil attributes, and then I guess what we really haven't talked about today is the difficulty, I suppose, of measuring these things. So we had to measure the drained upper limit and lower limit. So these are, people have done this before. They've measured the drained upper limit. So yeah, it's a labour-intensive job. So the alternative way to get to do these sorts of predict these variables is to use the petatransfer. So a petatransfer function is you've got relatively easier to measure variables, and they're related to these really difficult to measure properties. So this work by Jose Padarian in 2014 as part of his honours thesis was to look at this AppSoil database and to develop up some, because the AppSoil database has, they've really spent the time, they've measured these variables and related these to these relatively easier to measure variables, so bulk density, texture and CUC. So these are just mathematical functions really, and you apply these functions, and because we've got these really high resolution maps, we just apply these functions, and there's we can put some faith into these equations because they're developed on Australian soils in agricultural sort of settings. So there's, but they're not perfect, of course, but we can put some faith into them. And yeah, so we're developing up the LL15 and the drained upper limit. So and having this information is then critical as I move on to next about the calibration of the soil moisture sensors. Yeah, and because we've got this three-dimensionally in terms of the drained upper limit and the lower limit, we can work out the bucket size, so how much water is actually in that soil. the available water. This is not necessarily plant available, this is just available. And this is down to 140 centimetres. And this sort of aligns with sort of these general estimates that Mark was showing us before for that sort of hardened sort of districts. So they're not stupid estimates. Okay, so on to so that's the mapping. So now with the soil moisture sensor network. So the idea is to, because it is a research farm, is to facilitate research practices. We're looking at it's wired up as a digital farm. There's not just soil moisture sensor. There's all these other sensor networks across the farm, and it's really just sort of explore what we can use these sorts of technology for improving productivity of agriculture. So we're very lucky to have been able to have those resources to install this sensor network. So we've got 36 soil moisture sensors. So these are a HUSAT terrasond dielectric soil moisture sensor. This is a capacitance type probe, and these are developed by HUSAT. So they communicate to a base station, which is then distributed to a node via LoRaWAN. So each of these probes has an individual sensor down the length of that. So in our case, at these different depths, that's where the sensor is, and these are actually buried 30 centimetres under the soil surface. So that's just to avoid management, driving over the soils. You can still do normal cropping activities without disturbing the probe itself. And the output of these is a dielectric permittivity, and I'll talk a bit about that in a second. We've got 36 of these across the farm. Just this area here is our nearly established long-term cropping trial. So John Kirkyard is sort of leading this work. We've actually got 30 of these same sensors placed into these trials as well. So there's essentially 4 different cropping management philosophies being established here, and we're sort of wanting to looking at that over a long term time. So the soil moisture sensor calibration. So we call this the step 1 is a factory calibration. So these things are measuring the dielectric permittivity, and so in simple terms, this is just essentially the ability of a substance to hold an electric charge. Yep. So the dielectric constant. So it's a ratio of the permittivity of a substance to free space. So the permittivity, the dielectric constant of air is 1, and pure water is 80. Mineral soil is around 3. So where you've got a varying gradient of soil moisture, you'll have a relationship there with the permittivity. One of the so generally there's just a mathematical function that's developed to relate the dielectric permittivity to the soil moisture, volumetric soil moisture. One of the difficult things is that this permittivity is sensitive to a number of things, temperature being the main one, and pressure. So when you look at these raw data coming from the sensor, there's actually, if they're near the surface, you'll see a diurnal type variation. So a lot of these factory calibrations come with a soil temperature correction factor in these equations. So HUSAT, so they've got their own. We've got this calibration, so it's proprietary information, so I'm not going to share that. But this is particularly suited to. So Paul Hutchinson is, he's in communication, so it's suited to this particular area. So for the Boorowa area, is this particular equation, and it has a soil temperature correction in there as well. So if you buy a soil moisture sensor, you won't actually deal with the permittivity information. You'll just be no worries. You'll be what will come out is the factory calibrated theta, so the volumetric soil moisture, and a lot of people are happy with that. Just that's the factory, that's the soil moisture. But this time series goes from just about just the end of 2019 up to October last year. So we've really got the drought in print here, and you can see this moisture is sort of in the drought. We're really at the low end, the driest end, but it's not really just showing that on the sensor. But as we've been talking about before, this data is all relative. Yeah, so it's sort of they're not real values. You need to relate the relative to that. So you look at relative to time. So what we do is the second step is to link that information to some actual soil information, and so we're using a method here by Gash 2017. So basically, it's to rescale the upper and lower limits of the factory theta to corresponding estimates of the drained upper limit and lower limit. So there's only one equation in this talk, and that's it there. So that's this. It's a rescaling. So you've got the sensor, and then you're relating that to what the upper and lower limits are that you've got for that soil, and then you're scaling that. So you go from this to something that's looking more sensible. So that theta value in drought 2019, 2020. So we're really at the dry end of that bucket. In March we get that big influx of rain, and so forth, and then here we're getting the dry down of the crop and so forth. So we've actually got that sensor sort of directly responding. Well, it's making sense. Those numbers are actually making real sense. So the pros and cons. So readings of soil moisture from the sensor. So they're customised really to the local soil conditions. They're not just a factory calibration. So it actually means something. So you can convert that sensor into actual millimetres of available water. There's low physical effort required for estimation of DUL and LL15, but that's a con as well. One of the drawbacks is that because this is a modelled estimate, it's not actually a measurement. So you need to sort of take that into consideration. But nevertheless, it's a really handy process, and for calibrating a network of sensors, and where you've got sensors where you've got lots of inbuilt sensors down the probe, and you can do this pretty much automatically. And you can also update the various components of this calibration sequence as well through time. So if measurement is so similar concept, the approach it relies heavily on modelled estimates of the DUL and LL15. You need one of the things you need a long enough time series to be able to capture in that sensor the wet end and the dry end of that soil moisture characteristic that Richard was talking about before. So, but yeah, some of the things it's too much work. People are just happy to use that relative information. They're not really interested in getting those sensors into generating real values. They look and that's fine. But it's up to horses for courses, really. But yeah, the last couple of slides. Yeah. So basically, once you've got those sensors all sort of networked into the local soil conditions, then you can sort of build that into a spatial modelling framework. Because they're all sort of locally calibrated. We've got a spatial temporal model that's developed that's based on captures the soil variation in terms of texture, carbon, bulk density, and the landscape. And this model really can be run on it's using that soil moisture sensor data and then run on that daily time step. So basically, with those 36 sensors, so this model here that map there is just like one day, but you can sort of using that sensor data, you can sort of run this on a daily time step, and you can see up here we're in sort of right at the end of 2020.
That was rain.
Yeah, bit of rain. Yeah, and that's across the whole farm. You can it provides a really interesting way, I think, and you can sort of utilise this to, I reckon, to further our understanding of what's dry, where it's sitting in the landscape, where it's staying, where it's getting lost quicker. I think there's a unexplored sort of science here in terms of soil moisture, soil physics, when you're looking at these types of maps. It's raining up, so July, but you can see the wetting up pattern in 2020 is actually quite different to 2021. I noticed as well. So, and that's it. So yeah, last slide. Conclusions. Sorry about that. So yeah, I'll leave that there. But it basically, we're just getting these sensors to, putting them into some sense of reality so they can be they're real numbers that we're generating, and from that we can actually start to understand the spatial variation of soil moisture fluxes across the landscape.
Wonderful.
Thanks.
Thank you
So,
very much.